Now, to understand how we can modify a reaction to change anything about the kinetics of the reaction, we need to understand how reactions actually occur. And so what happens is that molecules collide. And sometimes molecules collide at the right orientation with sufficient energy and with the right molecules in order to actually get to the product. So just like when I'm looking at Legos, I could take the tops of two Legos and hit them together all day long with as much force as I possibly could, but they are never going to stick together because the orientation is not correct. Now, when we have molecules in a container or in a solution, what we find is those molecules are moving randomly around, and every once in a while, those molecules will collide at the right angle with sufficient energy with the right molecule, and we will actually get a product to form, the product that we want to form. Now, what we want to do is say, okay, well, I want this reaction to happen faster, or I want this reaction to happen slower. So we have to change the conditions so that we change the rate at which those collisions occur. Because in order to have an effective collision, which means in order to make the product, we have to have all of those parameters correct. Right molecule, right orientation, and with sufficient energy. And so what we want to do is change the conditions to increase the number of collisions if we want to increase the rate. If we increase the overall number of collisions, we're by default going to increase the number of effective collisions as well. So in that case, we're more likely to get to the product we want. So the three things that we're going to look at that we can kind of change, and usually change fairly easily, at least for the first two, are the different experimental conditions. So the first thing we can do is we can change the temperature. If I increase the temperature of a system, the molecules will start moving faster. Energy is, or temperature is just a measure of kinetic energy. So we increase the temperature, we increase the rate of molecular movement and molecular motion. When we do that, then what we see is that molecules are colliding more often. We're more likely to have a collision that is with the right molecule at the right angle with sufficient energy. It doesn't mean every collision is going to be effective. We're just trying to increase the chances that one of the collisions is effective, or increase the rate at which we have effective collisions. Same thing with amount of reactants, whether it be concentration or pressure, dealing with solutions or gases. But when we look at the amounts of reactants, if I increase the amounts of reactants, what I'm going to see is that effective collisions are going to happen more frequently. Imagine we were in the classroom and there were 5 people wandering randomly around the room. The odds of them colliding with one another are pretty low. However, if I then put 100 people in the same room, now I have more of my reactants there, more people, and they move randomly around the room, I'm going to increase the number of collisions that are occurring. And so by increasing the number of collisions that are occurring, I'm going to increase the number of product that is produced, the amount of product that is being produced. So controlling either temperature or amount of reactants can both be an effective way to either speed up or slow down a reaction. The third factor we look at is a catalyst, and a catalyst is a separate molecule that's added to a reaction mixture, and at the end of the reaction we still have that same substance present, so it is not consumed in the reaction. And the job of the catalyst is basically to make that reaction happen faster because it changes the path by which it happens. And we see catalysts all the time. In fact, our bodies depend on catalysts because without them, the bodily functions we need to happen, something as simple as breaking down glucose to produce energy, without catalysts, this would not happen on a time scale that would allow us to survive. So what we typically see is that the reaction rate depends on temperature. For many reactions, we're not looking at biological reactions. For many reactions, as we increase the temperature, we see a corresponding increase in the rate of the reaction. When we begin to look at biological reactions, and we'll talk more about enzymes later, but when we look at biological reactions, what we usually see is that there is a peak temperature at which something functions best. So if you look at the curve here, this first curve or peak here, what we're seeing is that its ideal temperature is somewhere around 27, 28 degrees Celsius. Below that, it's not ideal rate. Above that, it slows down, but that's when we kind of maximize that. Same thing here. This is around 38, 39 degrees Celsius. That reaction rate is peaking there, and it changes. And so every kind of reaction will have its own profile of what that looks like. For many non-biological reactions, it just continues to increase. For most biological reaction, there's a peak temperature where it is lower rate below that temperature and a lower rate above that temperature. So as we mentioned earlier, increasing the concentration increases the reaction rate. So if we have a low concentration, the odds are that we're going to have fewer collisions between the molecules of interest and fewer collisions at the right orientation with the right energy. If we increase the concentration, we're going to have more collisions overall. Therefore, we will have a greater number of collisions that meet all the requirements of reacting. The right molecules, the right orientation, and the right energy. And then we will be able to produce our product. So now we look at a catalyst, and catalysts again are what our body depends on in order to survive. And so what we see here is that we have the line in black here at the top, the solid line there. That is the profile of the reaction we looked at earlier. So we see there's some energy low, some energy high, and we see that the energy at the end is higher than the energy at the beginning. And so that tells us that the reaction is consuming energy and therefore will be endothermic because we have to put energy in. And that's strictly from the comparison of the starting materials and the ending materials. The activation energy, so without the catalyst, just a traditional mixture of our reactants, we have here this black line. What happens when we add a catalyst is that the energy at the beginning and the energy at the end don't change, but we see this peak is much lower. So the change in energy between products and reactants is the same, but with the catalyst, we actually have a lower activation energy. So now, when I look at the activation energy to this red line, okay, that's our activation energy. If I look for the uncatalyzed reaction, we go all the way up to there. So that's a bit higher activation energy. So if you're not a morning person and suddenly when your alarm goes off, your bed raises up and slides you out onto the floor, that would be your catalyst. It's making the same thing happen, but it's going to happen at a faster rate. You still start in bed, you still end up out of bed. You've just got an easier pathway to get there. Another way to look at this is if I'm going from Kentucky to California, there are lots of different ways I can go. If I go the long route, I can drive down to Texas and up here and on down, and it's going to take me a long time to get there. If I had a catalyst, so say maybe a plane, okay, that's going to take me directly there, that's going to shorten the time. So the catalysts speed up the reaction by changing the mechanism. They change the way it happens. So for example, if you're getting out of bed, you have to sit up, you turn, you put your feet on the floor, you stand up, and you're out of bed. If you're looking at the catalyst that's the bed lift dumping you onto the floor, the way you get out of bed is different, but you still end up out of bed. So the reactants and the products are exactly the same. What happens is how you get from the reactants to the products. So no, the catalyst will not affect a change in enthalpy. When we look at enthalpy, we're looking at the energy of the reactants and the energy of the products and the difference between those values. We're not worried about anything that happens in between, just the initial and final energy values. A catalyst will affect the activation energy, and that's in fact the job of the catalyst. It helps us bring this peak down to a lower level. And that's the job of the catalyst, is to make that easier for that reaction to happen by lowering the amount of energy it needs to kind of overcome that barrier. Sometimes this is also called an activation barrier. So we won't get into this too much, but enzymes, when we hear about those in our body, they are biological catalysts. And so what we have is that in our body, if we look at something like sucrase, is a catalyst that helps break down sucrose. If you are lactose intolerant, it is because you lack or don't have sufficient amounts of the enzyme lactase. Because our body can still break those things down, but it cannot break them down at a rate fast enough to be useful to us and to provide what we need when we need it. And so most of the biological functions and biological reactions that are happening in the body require the presence of an enzyme and require the presence of a specific enzyme. Our body makes enzymes that are very fine-tuned to the reaction for which they are acting as a catalyst. If I look at platinum as a common catalyst used in organic reactions, and I can use that in lots of different reactions. Sucrase is only good for the breakdown of sucrose into glucose and fructose. The only thing the catalyst changes in a chemical reaction is the activation energy. All of the other things don't change. We still make the same products. We still start with the same reactants. The energy of those things don't change. We're only changing that peak, that activation energy, or the amount of energy needed to get the reaction going.